Okay, today we're going to do a problem about the magnetic field of a coil and how it affects a compass. I'll start by reading the problem statement. A compass which originally points north is placed 11 centimeters from a coil of wire, which is composed of 8 turns of wire, of radius 2 centimeters as shown in the diagram. When the coil is connected to a battery, which is not shown, the compass deflects 18 degrees to the east. So, for the first part of this problem, we're asked to mark the direction and magnitude of the magnetic field at locations 1, locations 2, and location 3. Now, the relative magnitude, not just the magnitude. So, to do this, I first find by using the direction of the compass's deflection, find the magnetic field at that point. So because the compass deflects 18 degrees to the east, I know that the magnetic field at the point of the compass points to the east as well. Okay? Now, because of that, I know that at the other end of the coil, on this side of it, the magnetic field will be pointing the same way because of the right-hand rule. So, a coil of wire, the right-hand rule, is that the magnetic field points in the direction of your thumb if you curl your fingers towards the direction of current. Because I know the magnetic field is that way, I know at this coil that the current flows this way. So at the top, it's coming towards you, and at the bottom, the current's flowing into the board. So this works the same way at this point. Because the magnetic field is pointing this way, it'll point the same way at that point. Now, at the top, we don't use the right-hand rule for coils, we use the right-hand rule for normal wires. So, because it's pointing this way, the current, we can use another right-hand rule where we curl our finger around the wire, and then our thumb pointing in the direction of the current, and then our fingers will point in the direction of the magnetic field. So at the top of the wire, because of that we know that the current's going this way, I point my thumb this way, and now my fingers are curling to the left. And that's not the only thing contributing to this. We also look all over the wire, and so we'll see at the bottom that on the sides it'll cancel out, but on the top and the bottom is where they contribute. So at the top it'll be pointing to the left, but then at the bottom, because it's this right-hand rule, it's pointing into the screen, I use the right-hand rule this way, and we see that it points to the right. But because this is farther away, the magnetic field due to the top of the coil is more prominent than the one at the bottom, so it's still pointing to the left. But with only half the magnitude of the magnetic field at the points on axis with the coil of wire. So at the bottom, it's the same principle. The current is pointing this way. So then at this point, the current's pointing inwards, so the magnetic field is moving to the left. And at this point, the current's pointing outward, so the magnetic field is moving to the right. And they cancel each other out in such a way that the magnetic field at this point will be pointing to the left, but with half the magnitude of the magnetic fields at these 2 points. Okay, for the second part of the question, we're asked to find the magnitude of the conventional current running through the coil. Okay, so to do that, let's erase this. Okay, and I've got here the formula for magnetic field of a coil of wires. So that's mu naught over 4 pi times 2 n I a over z cubed. Okay, with z being the distance from the coil to the observation location. So in our case, z was 11 centimeters. Okay, and the radius of our wire, as we heard in the problem statement, was 2 centimeters. So the area would be pi times 2 centimeters squared. And n is the number of coils that are in the loop. So we knew that this had 8 coils. So n equals 8. Okay, so now we're solving for the current. This is all equal to B. Okay, mu naught over 4 pi is of course the constant, 10 to the negative 7. Okay, and yeah, so now we're solving for I. Now, if we remember from the compass, it was pointing 18 degrees to the east. Okay, so the formula that we can find magnetic field through that is that tangent of theta equals B equals magnetic field of the coil. Sorry. Over the magnetic field of the Earth. So we know that the magnetic field of the Earth is equal to 2 times 10 to the minus 5 Tesla. And because we know that theta equals 18 degrees, we can solve for the magnitude of the coil. So just by doing B Earth, 2 times 10 to the minus 5, times tangent of theta, we can solve for the magnetic field of the coil to equal 6.5 times 10 to the minus 6 Tesla. Okay? So now we know that that is the magnetic field at the point of the compass. And now using that value, we can plug back into this original formula for B and try to solve for I. Okay? So, let's do that. Okay, so after substituting in the values that I said earlier, we have 10 to the minus 7 times 2 times 8 times pi, and we'll convert all the centimeters to meters, so pi times 0.02 meters squared, and I over z cubed, and z which was 11 centimeters, so we use 0.11 cubed equals 6.5 times 10 to the minus 6 Tesla. Okay, and I should also note that this formula is the approximation for the magnetic field of a coil at a distance far enough away where the Z is much greater than R. Okay, this can only be used in that situation. And we know our Z was 11 centimeters and our R was 0.02 meter, was only 2 centimeters. So for this I use that approximation and it should work out fine. Okay, now if we shift all of these variables to try to solve for I, for the current, we find I equals 6.5 times 10 to the minus 6, and I'm going to take away the units for now and I'll replace them once we get the final solution, times 0.11 cubed over 10 to the minus 7 times 16, which is 2 times 8, times pi times 0.02 squared. Okay? And when we plug all of this in, we get the solution I equals 4.3 amps. And that is how you solve this problem.